Rachel.
And I'm Peyton.
We're Team 3, and we are developing a Battle Frog Rube Goldberg. We are making physics more fun in a complicated way. Today we will be discussing the background information from design phases 1 and 2. We will also be giving a project management update on our time. We will also be giving an overview on our models, both our mockup and our CAD. We will be giving an overview on the product architecture as well as the industrial design. We will also be discussing the economic proposals of both the assembly cost and the cost sheet. And finally, we will end with a reflection on how to improve our product. So some background from our previous design phases. We identified a need for a market that wanted interactive tools that would teach 11th grade SOL physics concepts. We learned that we had an 11-week project timeline in order to put our product on the market and to develop the product. We identified the customer needs as needing to be compact, affordable, and demonstrating the class topics in a clear and fun way. We identified our market segments into primary and secondary markets. On our primary market, we knew that we had to appeal to school administrators and department heads who were purchasing the products, as well as the classrooms who would be using them. Our secondary markets included community centers and libraries. In order to develop our product, we had to go through a concept generation and selection phase. And in this phase, we had to brainstorm using a 6-3-5 method, as well as discuss the best product possible with a gallery method. We also did external research on the product, in which we did an intellectual property research. Through this, we discovered patents that were similar to our product and what we could do that would not infringe on prior art. We also performed a failure modes and effect analysis in order to learn how our product behaved in the setting and to figure out how it would fail and how we could possibly improve the product. So project update, we are on time with our schedule. However, we knew that the slowest phase we would have was prototyping. So in order to stay on track, we decided to couple two tasks. We coupled prototyping with industrial design, and this saved us time, and we stayed on track for the rest of the 11-week timeline. So here's our product mockup, and this developed in our prototyping stage. Here we learned how to perform our failure modes and effect analysis because we were able to interact with how our product would actually work. From this, we learned that the rotating lever arm could easily fall off, as well as deflect the ball, and it could graze the ground, causing issues with the rotation and the overall performance of the product. We also had issues with our servo motor, in which that the calibration could fail us, and it could not perform as anticipated. This resulted in the highest issue of detection, while our grazing resulted in the highest risk priority number. Rachel will now talk a little bit about the CAD models as well as the overall product architecture.
So as you can see on the left, this is our CAD model of our entire product, and as you can see, it's very simple. We really only have three external components. So here is the rotating contraption in the middle, and the blue part is the pathway that will guide the ball along as the contraption rotates. And underneath the rotating contraption are electronic components. So we have our servo motor, our Arduino, and any wires and breadboard under there. And then on the right, you can see the another visual of the rotating contraption, which is our primary component in the product, and it is dimensioned to show the size of our actual model. For the product architecture, we decided to categorize the product into two different chunks, so the electrical components and the mechanical components. For the electrical components, we had 4 different elements, and these elements were the servo motor, the wires and breadboard, the Arduino, and the battery. And for these components, we had all of these stored underneath the rotating contraption, and then we had a user input as one of the functions within the electrical components chunk, and this led the student would be able to input their actual calculated velocity and their rotational velocity, and then this would lead to the action of the mechanical components. So for these, the rotating contraption, or the contraption in the center, would rotate and guide the ball along the path, and then there would be an output for the translational velocity based on the other chunk. For the industrial design, our primary focus was on the ergonomics rather than the aesthetics, and this is because this was a product that was supposed to simply convey physics concepts. So the point of our product was to be able to convey difficult concepts in an easy and concise manner, and so for that reason we wanted ease of use to be of very high importance, because we wanted the student to be focused less on how to use the product and also how to maintain the product, and more on the types of concepts that it should be conveying. And with that, because the point was to be used as a learning tool, we wanted as many students to use as possible, so quantity of interaction was also very highly rated on importance. And this, for aesthetics, this was team motivation, and the pride and ownership were rated the lowest because aesthetics was the least of our important factors.
For the assembly costs, the team thought about the packaging process to determine the cost of each part in the assembly. Then we had estimated and assumed based off of real life examples and experiences of each part of the product, and how it would occur and when we would use it. The cost was determined by the assembly costs per minute and then multiplied by the total time. So each of the parts had a time to it, and then total it up would make the cost times the minute. Some examples included packing the ball into the box, which would be a total of 15 seconds, and this was one of the shorter amounts of times of the parts. A larger amount of time of the parts would be to pack the breadboard in with the wires for the packaging, and that would be a total of 50 seconds. Also, for the economics part of the cost sheet, we had the bill of materials, which showed all the parts that were included in our product and the cost for them. This estimated the price for each part of the BRG, and then the team had determined that the total cost for one whole BRG would be around $192.25, and this includes all the materials and the packaging process. For example, we had the Arduino at a price of $25. We also had a smaller price of the cardboard, which we use for our product, at $2. Another cost that we had included was for 3D printing, and this included all of the parts for 3D printing and all the materials that came with it, and we had put that at a cost of $15. Moving forward with our design, we came up with improvements that we thought would make our product better in BRG and would make it in the future help more students learn. Some of the improvements that we had included were improvements on the materials, improvements for the angle of the lever arm, as well as improving the accuracy of the servo motor. When we improved the materials, that would help with the transition of the ping pong ball, and it would help with smoothing out the transition, as well as when we improved the angle of the lever arm, it would improve the consistency and ensure consistency from rotational to translational velocity. Improvements of the accuracy of the servo motor would prevent error, and as well as any interferences that the servo motor would cause to the movement of the ping pong ball. And so in these improvements, if we were to have the time as well as the money to move forward with our product, these are the things that we would make at first better.